Alright folks, welcome to Geometries for Squares. Today we're going to cover lesson 6.6. And it's a pretty short lesson, but I did want to lay a little bit of groundwork because it's kind of abstract and can be a little confusing if we don't kind of take a minute to figure it out. So if we were to take any sort of parallelogram, and actually any shape really. Here we've got a square, nice even square, and we wanted to kind of talk about it a little bit. Here we don't have any markings, right? We don't know what its size is. We don't even necessarily know that it's exactly a square. We don't have marks to show that it has 90-degree angles. We don't have any information in here. So we can start to gather some information. If we wanted to determine the sides of this quadrilateral, we could bring in a ruler, right? We could bring this bad boy over here and we could measure, and it looks like, what about 5.1, maybe 5.2 if we slide this over here, a little more. And then we could measure the other sides, right? We could take this and spin it around, come measure this other side. Good bit of work though, right? We're measuring, we're moving, we're doing all that kind of stuff. So what if we did something a little bit differently? Let's bring this down. Oh. Alright, so what if we did something a little bit differently? Let's bring this down and let's look at just a regular Cartesian coordinate plane, right? A graphing plane. And we can put this anywhere, right? It doesn't change the fact that it's a square. It could be a square up here, it could be a square over here, it could be a square here. And we can see that by, if we line this up nicely, we can see that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 units across this way. 1, 2, 3, 4, 5, 6, 7, 8, 9 units across this way. And we can see that these follow the grid marks there and do form 90-degree angles. So we do in fact have a square. We can see that just as easily if our square is placed, starting at the origin up here, or if we have it down here, wherever it happens to be. Now they do this quite often in geometry where they take a shape and they introduce it to a coordinate system so that we can identify and give these things coordinates. So if we were looking at this square, we could then say, okay, well here's our square, and this point, this corner of the square is at point 1, 2, 3, 4, 3. So the coordinates here would be 4, 3. We could identify a coordinate here, right? It would be -5, 3. So we could say the coordinates here, -5, 3. Do the same thing for all 4 of the corners of our shape. All right, this one would be what? 4, -6. Right, 1, 2, 3, 4, 5, 6. And this one's going to be -5, -5, -6. Right, so there are 4 coordinates for our square. And if that's all we had, if we couldn't really see the shape even, right, if we were to get rid of the shape, right, this would still have 4 coordinates. All right, so even if we get rid of this shape, we can still see that we have 4 coordinates here that we could determine was a square. If they just gave us these coordinates, we could then use the distance formula to show that this length is equal to this length. We could show, use the distance formula to show that this length is equal to this length. We could use the, find the diagonals of these two. Right? So we could find this diagonal and find this diagonal and find their midpoints and show that they bisect. There's lots of things that we could do with these coordinates just to prove that we do in fact have a square. So this idea of taking a shape and putting it into the coordinate system really gives us an advantage because it allows us to give numerical value to not just the length. If we were just to talk about a square, we could really only talk about the length of its sides and the angles. But if we introduce it to a coordinate system like this, we can actually see that now we can not only talk about the length of the sides, but we can talk about the location of each corner. Right? So we've given each point, each edge on there, a location. So as we go into this first example, it looks like a hot mess, right? This thing, we've got A's and B's and W's and C's, and there's just stuff everywhere. It's a total mess. But all they're saying, the A, this A and the C and the E and the O, those are just kind of to get in the way, right? But if we look, the question is really talking about TWVU, right? That's our shape there, TWVU, the four corners of our shape. And they give us coordinates for those. I don't want the little A's and the C's and the B's and all this mess to get you tripped up. All they're doing is, instead of giving you coordinates like we saw here, instead of giving you -5, 3, and 4, 3 numerically, they're just giving you variables. They're just trying to make it a little more difficult. So instead of -4, 3, we're getting A, B. Right? So each of these now has coordinates. There's just quite a few variables in there. So what they want us to do is they want us to prove that this is a parallelogram by showing that the opposite sides of this shape are going to be congruent. So if we take a look at this, we know that if both pairs of opposite sides are congruent, then it's going to be a quadrilateral. And they say theorem 6.5. Again, this goes back to what we talked about in class, where the numbers really don't matter as long as you can say if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. No need to know that it's theorem 6.5. Just know that it is a theorem. Alright, so we can prove this by showing that TW is equal to VU, right? This side up here, and we can, let's mark these, give them a little bit of color. So if we show that TW here is congruent to VU here, that's one step. And then the other step would be if we show that WV, this side, was congruent to TU, this opposite side. So if we can do that, then we can prove that that shape, TWVU, is a parallelogram, right? So WV and TU are the other two sides that we need to show are congruent. Well, we have coordinates, and we're concerned about congruency of these sides, so we need to find their distance, right? We need to find the length of the side so we can find the distance between 2 points. So this goes way back. You guys probably haven't used this for quite some time, but using that distance formula, the one that's just a modification of Pythagorean theorem. And if we look at our 4 points, again, they all have coordinates. They're just really funny because they're all variables. So the coordinates for T are A, B. The coordinates for W are A plus C and B plus D. Coordinates for V are C plus E and D. And then U, the coordinates are E and 0. So we're just going to take that distance formula, right, and we're going to take the difference between the two y values. So first they're going to do T and W. I think they'll do actually the x values first. So they'll take the x value for W and they'll subtract the x value for T, and then they'll square it. And then they'll take the y value for W and subtract the y value for T, right? Y value from here minus the y value from here, square that. Put that all together. Once we simplify that, our b's cancel. Right? The b's cancel here. B minus b. The a's cancel. We get a minus a. And we're just left with c squared plus d squared. Right? All in the square root. Again, just plugging in variables. Don't let the fact that it's a variable and not a number get you tripped up. Just follow the same pattern, the same rules. As we move on to VU, we can see pretty much the same thing. We're going to take the coordinates from V and the coordinates from U. So they'll take U and they'll subtract V, and then U and then subtract V for both X and for Y. And here our 0 drops out, and again we get a little canceling. E minus E, those cancel out, and so we again just get C squared plus D squared. So we've covered our first step. TW and VU, when we plugged in the distance formula, both give us the same answer, the square root of c squared plus d squared. No need to actually know what it is, just based on the fact that they're the same means that those two sides are congruent. Then we can move on to the other two. So we can take W and V. Again, they're going to take the x coordinate from W, subtract the x coordinate from V, then subtract from W for x. And then they're going to do the same for y. Again, we get some cancellation here, d minus d. And here we get c minus c. Right, so in the end, we're just left with a minus e squared plus b squared under our radical. And then when we do t and u, same thing, we're going to get a minus e when we take t, then u, and then b minus 0. The 0 drops out, and we're just left with a minus e squared plus b squared, which is the same as wv. So we've shown that these two were congruent. Now we've just shown that these two are congruent, which means if both pairs of opposite sides are congruent, then we know that it must be a parallelogram, right? So TWVU is in fact a parallelogram. Just a little hint, when you move on to this quick check, now they want you to look at the parallelogram and use the midpoints, right? Find the midpoints of the diagonals to show that it's a parallelogram. So you're going to use this same figure with these same coordinates, right? Here are the coordinates here, but instead of finding the distance between t and w, you're going to find the midpoint between t and v. So you may have to go back and look up that midpoint formula to be able to find the midpoint between t and v and find the midpoint between w and u. And what you're looking to do is prove that, in fact, the two midpoints are the same. So give that quick check a try as part of your homework tonight. All right, moving on to this second example, and this is the last example. We have another parallelogram. This time, again, it's in a coordinate plane. Now we're in the second quadrant, over in the negative side of things. Here's our origin down here. And the directions ask us to use the properties of a parallelogram, specifically OCBA, to find the missing coordinates. So we can see we've got an x here, a p here, a q. So they're using variables here, but the missing coordinates that they're referring to are the coordinates for b. So again, this is another situation where we're not necessarily using specific values. I mean, we do have a 0 in here, but we're going to be using variables to identify these coordinates. They just want to know what are the coordinates of b. So that's what they mean by missing coordinates here. So if we take a look, whenever we take a crack at these things, we can always use, it's an example, so it's there for a reason to show us how to do it. So if we continue to read on, it says the vertex O is the origin with coordinates. Well, we should know that the coordinates of the origin are always going to be here, where the x and y axes cross. And the coordinates there are going to be 0, 0. So if this is our starting point, and we can write that in there, that this is, 0, 0, just for reference. So that's our starting point. And then it says because A is p units to the left of point O. So if we look at big A, our point here, it's p units to the left. We can see that negative p is the coordinate here, which just means that if we drop this, I'm not going to be able to do a very straight line here. If we drop this line down here, that means that this little bit here, that's p units. But it's p units to the left of the y-axis, so we get negative p as our x-coordinate. Then it says point B must also be p units. So all they're saying is that if we drop a line down here from point B, they're saying that this little space here is also going to be p units. because this is p units, this space here must also be p units because it is a parallelogram. So if that's the case, right, so if this is also p units left of the point of C, well, we know that the first coordinate of B is going to be this from here all the way out to C, and we know that that's x units, or negative x units, and we know that this is negative p units. Right, so if we look at that combined, it's going to be negative x, right? Negative x is this space here. Right, we're moving to the left of the y-axis, so these are all negative. So we're negative x units. We can put negatives out in front of all of these. Negative x units from here to C, and then negative p units from C out to the x-coordinate of B. So the first coordinate for our point B is going to be negative p minus x. So then from there, once we found our x-coordinate, now we just need to find the y-coordinate here. Right? Well, let's think about this. If we let's get some of this stuff that we put in here out of the way. Again, if you need that, you can rewind back. But let's take a look now. Y-coordinate means we're basically just dropping a line here, dropping a line here to the y-axis, and we can just see right away that that passes through point A. So we know that point B and point A should have the same y-coordinate. Another way that we can look at this, the book says because AB and CO, so this line up here AB and this line down here CO, because they're parallel, it is a parallelogram, so these two are going to be parallel. We can see that CO is horizontal. It runs directly along the x-axis. So we know that BA must also be horizontal, which means that they should have the same y-coordinate. So in the end, when we look at these, AB is also horizontal, and so they're going to have the same y-coordinate, which is Q. So we can write Q in there, right? If this one is at Q on the y-axis, then B must also be at Q. So there's our second coordinate. The origin is 0, 0. They consider that missing, but we already found that up there. And point B is at negative P, negative X, or negative P minus X, and then Q for the y-coordinate. So again, don't get discouraged or freaked out because these are letters in here. Just do as you normally would, right? If they were numbers, do the same thing with the letters. And then if it becomes a problem at some point, then you can try to think of something else. But usually if you just treat the letters just as you would the numbers, you're going to end up with the correct answer. Alright, so that's it for the lesson. You do need to do the quick check as well, so the second quick check. And really, again, it just mirrors that previous example that we looked at. So again, we have a parallelogram, and it's on the coordinate plane, and we've got 2 points here, and we're missing the coordinates here, and we're missing the coordinates here, and you essentially just need to do the same thing that we just did. So give that a little bit of practice for the quick check, and then we will jump into the full-on practice material tomorrow.